Hello, friends. Welcome to Science Talk. I'm your host, Joe Massa. I want to discuss with you what we see right here: rapid seafloor changes associated with the degradation of Arctic submarine permafrost. It's an article that came out on Pi Day of this year, March 14th. And we have Charles Paul, Scott Dallimore, and several other authors. And let's look at the significance. Now, I will leave the URL link in the comments section. Uh, this paper does an extreme deep dive and it gets really wonky. What I'm going to do is, after I share with you the significance in the abstract, I'm going to move over to the EOS online publication of this paper, where they do a very nice, succinct summary of the work here. So, what is the significance? Temperature increases in Arctic regions have focused attention on permafrost degradation on land, whereas little is known about the dynamics of extensive glacial age. Permafrost bodies now submerge under the vast Arctic continental shelves. Repeated high-resolution bathymetric surveys show that extraordinarily rapid morphologic changes are occurring at the edge of the continental slope of the Canadian Beaufort Sea along what was once the seaward limit of relic Pleistocene permafrost. How widespread similar changes are on the Arctic shelves is unknown, as this is one of the first areas in the Arctic subjected to multiple multi-beam bathymetric surveys. Rapid morphological changes associated with active submarine permafrost thawing may be an important process in sculpturing the seafloor in other submarine permafrost settings. So basically, they're trying to better understand how much of the permafrost is degrading. And that's going to change the morphology of the substrate, basically. Now, I want to point out what to talk about here: the edge of the continental slope. That phrase right there. Okay. That's basically the transition from the continental shelf to the slope, where the slope then becomes a steeper angle that then takes you to the bottom, to the basin. I did a video some time ago where I looked at basically a thermogenic source of methane at the shelf break, or where the slope begins. And that what has been documented is massive explosions of methane. So let's look at the abstract. Repeated high-resolution bathymetric surveys of the shelf edge of the Canadian Beaufort Sea during 2 to 9 year long survey intervals reveal rapid morphological changes. New steep-sided depressions up to 28 meters in depth developed, and a lateral retreat along scarp faces occurred at multiple sites. These morphological changes appeared between 120 meters and 150-meter water depth, near the maximum limit of the submerged glacial age permafrost, and are attributed to permafrost thawing, where ascending groundwater is concentrated along the relic permafrost boundary. The groundwater is produced by the regional thawing of the permafrost base due to the shift in the geothermal gradient as a result of the interglacial transgression of the shelf. In contrast, where groundwater discharge is reduced, sediments freeze at the ambient sea bottom temperature of approximately minus 1.4 C. The consequent expansion of freezing sediment creates ice core topographic highs or pingos, which are particularly abundant adjacent to the discharge area. Now, it's interesting to see him use the word pingo here. Pingo is a well known feature of the Arctic landscape. And basically, you can be traveling along and see, oh, it looks like a mound or a bit of a dome. And that's basically elevated ground, but it's filled with ice in the middle. So when the ice starts to melt, it then collapses. So then you get a depression in the ground. And we're seeing this more and more in the Arctic. And now it looks like on the seafloor. So let's switch over to the summary here that was published on the EO site, which is from AGU. And if you look at this paper here, okay, it's published in the Proceedings of the National Academy of Science, which is basically a division of AGU. Okay, so it's all tied together. So let's groundwater flow may contribute to submarine permafrost thaw. New detailed surveys in the Beaufort Sea reveal a seafloor depression the size of a city block associated with permafrost thaw and likely influence the movement of groundwater below. Now, this is on the Beaufort Sea, so this is the North American side. Keep in mind that Natalia Shakova, Igor Semiletov have done extensive work on the Eurasian side, primarily in the East Siberian and Laptev Seas. Now, the work I just cited a moment ago about looking at the methane explosions at the shelf break was done by another group of researchers, and that was in the Laptev Sea. So when you actually look at the shelf system, the Eurasian side tends to have a more extensive shelf system. It proceeds further away from shoreline, so it's a bit more extensive. But we still have a shelf system, especially in the Chukchi and Beaufort Sea areas. Okay, so what we see here is a ship-mounted multi-beam sensor. They also use autonomous underwater vehicles, sometimes ROVs, remotely operated vehicles. Oh, and a remotely operated vehicle to prepare detailed maps of the seafloor in the Canadian Beaufort Sea. So this is oceanography being done here, folks. The Arctic is melting, the Arctic is thawing. Warming temperatures are thawing the permafrost. Permafrost is the basic frozen ground layer. And humans have built communities on the permafrost. Permafrost is thawing. Those communities are in trouble because now the ground starts, heaving and sinking and breaking. Your buildings start falling into the ground. It becomes uninhabitable. So the thing's happening. There are many open questions about permafrost degradation on land, like exactly how much carbon is entering the atmosphere, the impacts on climate change. Of course, and there's a lot of studies trying to estimate those releases. But there are even more unknowns about what's happening with the permafrost submerged in the Arctic Ocean. Yep. And here they reference that. A new study published in Proceedings of the National Academy of Sciences of the USA describes some of submarine permafrost large changes at the continental shelf edge and slope of the Canadian Beaufort Sea from 2010 to 2019, basically a 10-year period. Over the study period, the international team of scientists detected the formation of at least one new depression, which is equivalent in volume to a New York City block composed of six-story buildings, said Charlie Paul, a marine geologist at the Monterey Bay Aquarium Research Institute, co-author of the new research. That's this gentleman right there. And let's see if I can't really enlarge this. Okay. Repeated surveys of the Arctic shelf edge in the Beaufort Sea revealed a massive depression that developed in this time year period. And you can see it outlined here. 74 meters seems to be the width, 220 meters the length, 24 meters in depth. So, rather substantive. And they had a statement from Jennifer Frederick, who's a computational geoscientist at the Sandia National Laboratory, not involved in the study, said, well, I guess the area is a bit more dynamic than we thought. So in 2010, researchers mapped a 95-kilometer stretch of the Arctic shelf edge in Canadian Beaufort Sea, about 180 kilometers offshore. The ship-based survey uncovered unusually rough seafloor between 120 and 200 meters below the surface at the transition between the shelf edge and the slope, where the rate of descent increases substantially. Over the next several years, the team of scientists scrutinized the same area multiple times by performing additional surveys using ship-mounted multi-beam sonars and collecting higher resolution data with autonomous underwater vehicles. These guys. The approach enabled them to track changes in seafloor morphology over time. So basically, in 2010, you map it, you recreate a 3D representation, and you got a baseline. And then you go back and compare. And that's exactly what they did here. The team identified distinct bands of features. Oval-shaped depressions were situated in a region of rough denuded terrain. The team detected features at lower depths resembling pingos, ice-cored hills that dot the Arctic landscape, as I described to you at the outset of this video. It's a slow process. Unlike what's happened in permafrost on land, the researchers don't think submarine permafrost in the Beaufort Sea is thawing due to warming temperatures because the waters bathing the depression pocked region are about minus 1.4 degrees C. That does not melt the permafrost or thaw it out, melt the ice, thaw the permafrost. So instead, the researchers propose that groundwater is slowly moving a few hundred millimeters per year. Okay, so a few hundred millimeters, that might be 10 millimeters is a centimeter. So 100 millimeters is 10 centimeters. So a few 100 millimeters could be like a meter a year. So they're proposing that this groundwater is slowly moving. It's moving under the permafrost and warming it from underneath. Think of the warming ocean waters melting the ice from underneath the ice, say around Antarctica or in the Arctic Ocean itself. So as the permafrost thaws, it can periodically collapse to produce the large depressions detected by the team. So in other words, go up to this image here, this could have been level with the rest of the terrain, maybe even a little higher. You melt out this water and thump, the land subsides. And this is probably like a pingo that collapsed. Just speculating there. This is an area where very small changes, but sustained over long periods of time, may be playing out big effects. Paul said the team estimated that the rough terrain along the edge of the continental shelf took about 1,150 years to form. Frederick said the author's analyses seem to support conclusions from a 2015 modeling study that she did co-author, which proposed that groundwater could be flowing offshore to this area. The pingo-like features on the seafloor, for example, align with where the model expected groundwater to rise up to the seafloor, depending on the balance of water temperature, salinity, and flow rate. The circular features could appear when groundwater freezes as it approaches the colder seafloor. One of the predictions in the model was that this groundwater flow is still occurring today. And so this is a very interesting development. So what does that mean? Okay, so at 150 meters, okay, you may not have because the warm water that comes in, and this is on the North American side. So we're talking about Pacific water coming in. Pacific water, when it comes in, does not reach that depth of 120 to 200 meters. It may at 120, but definitely not 200. Yeah. Even on the Atlantic side, the water is pretty much coming in at about the 100-meter level, plus or minus, and it flows around. It gradually starts shoaling. But the point here is that the oceanic water flowing in is too cold to directly be thawing out the permafrost. But it's obviously creating a change in mechanism that groundwater is now increasing its flow rate, possibly its volume, so that the groundwater seeping underneath is sufficiently warm enough to melt the ice, thaw the permafrost, which means that the groundwater, which presumably has no salinity, is above 0°C. Melt enough of the permafrost and you get slumping. But of course, what's the major implication of this? Well, you already know the answer to this. It's methane. How much methane is being released from such mechanisms, and how widespread is this kind of occurrence taking place? Those are questions that need to be answered. But you couple this work with the work that Natalia and Igor have done, and you can start get a better handle on not only the rate of which the thawing is occurring, but you get an estimation of the volume and therefore how much methane gets actually released. And when it's released into the water, is it absorbed? Does it dissolve in solution with the ocean? Or does it, if it's so much of it, like I discussed in the Laptev ice edge sea methane video, you can have these sudden explosions and they go right through the water column into the atmosphere. So these are some questions that need to be answered, need to get a better handle on. But as everything else, it means what? More methane in the atmosphere. We all know that's not good. So, as I said, I'll leave the URL in the comments section, but I just wanted to, bring this quick little topic to your attention. And, we all know what the implications from this are. So, until next time.